What if one of the loudest, dirtiest machines in our cities could suddenly operate in near silence? Well, that's the big promise of the new hybrid cement mixer. But, an idea is one thing. Proving it's tough enough, reliable enough, and most importantly, safe enough for the real world, that is a massive engineering challenge. So today, we're going to pull back the curtain on that entire journey, from a purely digital concept all the way to a fully validated, road-ready revolution. Okay, let's just jump right in. On the left, you've got the construction site staple we all know and, well, we all hear it. We're talking noise levels over 95 decibels. That is louder than a subway train roaring past you. Now, look at the right. The hybrid system, it's humming along at under 65 decibels. That's the difference between having to shout to be heard and just having a normal conversation. So this isn't just a minor upgrade. It's a complete reinvention. And proving this thing actually works is the real engineering story. So here's our roadmap for this explainer. We're going to cover 5 critical stages. We'll start with why this was even necessary, then dive into the digital and real-world testing gauntlets. After that, we'll see how it passes the global safety tests, and we'll finish up with the final engineering verdict. Right, first things first. Why go to all this trouble in the first place? Well, the core of the problem is a massive, fundamental inefficiency that's been built into every traditional cement mixer on the road for decades. Think about this for a second. For nearly half its life, that giant diesel engine isn't moving the truck an inch. Nope, it's just sitting there, idling, burning fuel just to spin the drum. This is where the magic of the P2 hybrid system with an electric power takeoff, or ePTO, comes in. In simple terms, this architecture lets us finally separate the job of driving the truck from the job of spinning the drum. So the engine can shut off completely on site, which saves a ton of fuel and kills that constant roar, while a quiet, powerful electric motor takes over the real work. So how do you even start? Well, before you bend a single piece of metal, you have to prove the logic is sound. And this is where modern engineering really begins, not in a dusty workshop, but in a world of pure simulation, where we can test the system to its absolute limits without any physical risk at all. The whole validation process is guided by what we in the industry call the V model. You can think of it as a journey from the purely abstract, on the left, down to the physically real at the bottom, and back up. We start with just the software, testing its logic against a computer model of the truck. Then we introduce the real hardware into that simulation. And only when that is perfected do we go and build a full prototype for real-world testing. Now that middle step, HIL, or hardware in the loop, this is absolutely critical. It's the bridge that connects the digital blueprint to the physical world. We take the actual brain of the hybrid system, the supervisory control unit, or SCU, and we plug it into this incredibly powerful simulator that tricks it into thinking it's connected to the entire truck, from the high-voltage battery right down to the wheels. And doing this lets us ask the really, really tough questions, the questions you never ever want to answer for the first time on a real vehicle out on the road. Like, for instance, what happens if the accelerator pedal signal just disappears while the truck is churning tons of concrete in the drum? What does the system do? In the HEAL lab, we can find out, safely. We digitally inject these faults right into the system. What if a battery contactor fails to close? Or a critical sensor starts sending junk data? We run literally hundreds of these nightmare scenarios to make sure the controller's logic is absolutely flawless. No matter what goes wrong, the system has to be smart enough to default to a safe state, which means instantly shutting down the high-voltage power and bringing that drum to a controlled stop. No exceptions. Okay, so once the system has proven itself time and time again in the digital realm, it's finally time to face reality. The first prototype is assembled, and it heads straight to the proving grounds to face a series of absolutely brutal physical challenges. And when I say the targets are brutal, I am not kidding. The electric drive has to generate 64,000 Newton meters of torque. To put that into perspective for you, that's more raw twisting force than a dozen high-performance sports cars combined, all just to churn the densest, heaviest concrete imaginable. The battery has to stay perfectly stable, the whole system has to survive bone-jarring vibrations, and, get this, it has to withstand a direct blast from a high-pressure 80°C water jet. We're simulating the daily power wash it's going to get on a real construction site. Now, this isn't just a one-time pass-fail test. It's a continuous feedback loop. Every single piece of data from the proving ground, every temperature reading, every vibration sensor, every amp of current is beamed right back to the engineers. They use this real-world information to constantly refine the software, to fine-tune the calibration, squeezing out every last drop of efficiency and performance.
So after the truck has survived the physical gauntlet, the final hurdle appears, and it is a big one. It's navigating the incredibly complex and often contradictory world of global safety regulations. Because a machine isn't truly market-ready until it's certified to be safe everywhere it might be sold.
And wow, this slide perfectly illustrates the challenge. Just look at that top row, thermal event. Europe says you need to give the driver a 5-minute warning if a battery starts to dangerously overheat. But China, they're much stricter. They demand absolutely no fire and no explosion for 2 full hours. And then the US focuses mainly on safety after a crash. You can't just design for one, you have to engineer a single system that's robust enough to satisfy them all simultaneously. Let's just zoom in on that European standard for a moment, because this requirement from ECE R100 is a total game changer. It means the battery management system can't just monitor the whole battery pack as one big block. No, it means the intelligence to detect a single, tiny battery cell out of thousands, beginning to fail and immediately sound the alarm. That is an incredible technical challenge.
So why does this matter so much? Because those 5 minutes, they are everything. That's the time a driver needs to safely pull over, get out of the vehicle, and move to a safe distance. This isn't just some line item in an engineering spec sheet. It is a life-saving design requirement. It's what turns a potential catastrophe into a controllable, manageable incident. And beyond just battery safety, there's another sort of invisible challenge: electromagnetic compatibility, or EMC. Think of it like this: that powerful 400-volt system that's driving the drum can create a lot of electrical noise or static. We have to prove conclusively that this electrical noise doesn't interfere with the truck's sensitive 24-volt brain and nervous system. It's like making sure you can hear a whisper right next to a rock concert. So, after all the simulations, all the physical abuse, and all the regulatory hurdles, the entire multi-year journey is distilled down into a final set of documents. This is the engineering report card. This is the ultimate proof of success. The first and most important of these is the DVPNR. This is the master document. You can think of it as the Bible for the entire project. It lists every single requirement, every test that was planned, and it meticulously records the final pass or fail result for each one. It is the definitive evidence that the engineering was done and done right. Next up, you get the safety certification checklist. This is basically the vehicle's global passport. It's the final scorecard confirming that the vehicle has officially passed all those unique and demanding high-voltage safety rules for Europe, for the US, and for China. And you can see it also includes functional safety, and even the PIAC Quiet Truck certification, proving it's ready for any market in the world.
And finally, the performance report. And really, this is what it all comes down to for the end user. The data proves it all out. Over 25% in fuel savings, a massive reduction in on-site noise pollution, and a significant long-term benefit to the total cost of ownership. The engineering didn't just create a new machine, it created a fundamentally better business case. So there you have it. We've seen how this incredible level of validation engineering can transform a common, everyday piece of industrial machinery into something smarter, safer, and just vastly more efficient. It really makes you wonder, doesn't it? What other invisible industrial giants that we all rely on every single day are about to get their own high-tech revolution?